We all have a thirst for wonder. It's a deeply human quality. Carl Sagan. We've been staring up at the night sky since we first descended from the trees, and over the ages, we've attached stories and cultural mythologies to the glimmering lights that we saw there. We noticed that a few of the stars we saw in the night sky didn't move with the rest of the celestial sphere. These others, these wanderers, had a habit of being in a different spot each night. Somehow these wandering stars were a little bit different. Knowing what we know now, the most distant of these that we could see with the naked eye was Saturn. In terms of the way we have thought about it, Saturn has lived multiple lives throughout the ages, from elderly deity and master of time to a puzzling fuzzy blob sketch at the birth of the telescope, to, as we know it today, the majestic ringed gas giant that seems to gain moons every single time we look at it. As we progress in leaps and bounds out into the darkness, it became quickly obvious that sending robotic emissaries is going to be both much easier and safer than it is to send our fragile bodies out into the void in order to get to know our cosmic backyard. Cassini-Huygens was one of those emissaries. A billion-dollar flagship-class mission to the outer planets, its brethren include Galileo, Voyager, and Viking. The mission had two main elements: the Saturn orbiter built by NASA and ASI, and the ESA-led Titan atmospheric descent probe. During conception, the mission was simply called Saturn Orbiter Titan Probe. The name evolved through many iterations and focus groups, but the choice was pretty obvious. The American orbiter would be known as Cassini, and the lander would be called Huygens. The cosmos is a vast and wondrous place, filled with mysteries waiting to be unravelled. Among the countless minds who have dared examine the heavens, a few stand out. One such mind is Giovanni Domenico Cassini. Born on the 8th of June 1625 in the vibrant city of Perinaldo, Italy, Cassini would go on to bridge the realms of art and science, leaving an incredible mark on the understanding of the universe. Being attracted to the heavens early in life, Cassini was pulled toward a career in astrology, which over the course of his lifetime was starting to be seen as the pseudoscience we now know it to be today. Whilst astrology is most definitely a scientific dead end, it did lead to our modern conception of astronomy and Cassini's first job in the field. Marcus Cornelio Malvasia, a senator of Bologna who had a deep passion for the night sky, even though he was a bit misguided, was building an observatory in the region and invited Cassini to work at the facility. He observed and detailed the moons and atmosphere of Jupiter and measured their orbits with remarkable precision. He is a contender, along with Robert Hooke, for the discoverer of the Great Red Spot. With this meticulous attention to detail, he revealed the true scale of our solar system. Working with a collaborating astronomer in French Guiana and using a combination of triangulation and parallax, they were able to calculate the rotation of Mars down to a few minutes of what they know it today, and also get a reasonably accurate measurement of the width of the orbits of the planets. But Cassini's journey was just beginning. In 1671, he was invited to Paris by King Louis XIV to be a director of a new observatory, Observatoire de Paris, where he would lead a new era of astronomical exploration. It was here that his career truly blossomed. During this time, he made some of his most famous discoveries: Saturn's moons Iapetus, Rhea, Tethys, and Dione. He also spent a lot of time observing Saturn and puzzling over the constitution of the rings, being the first to theorize that it must be comprised of many smaller bodies orbiting in unison. A large gap in Saturn's rings now bears his name, known as the Cassini division. Like many of the early scientific pioneers of this period, Cassini was interested in many disciplines. While he spent a great deal of time in celestial pondering, he was also known for his work with the cartography of France, again working closely with King Louis, who once joked about Cassini having cost him more land through accurate mapping than all the opposing armies he'd ever faced off against put together. Giovanni Domenico Cassini passed away in 1712, but his legacy lives on. In the pages of science history, he is not merely a name, but he is a beacon of the human spirit's quest for knowledge. As we continue to explore the universe, we carry with us the echoes of his discoveries guiding our journey into the unknown. Imagine, if you will, a time when the stars' secrets had yet to be discovered. A time in the 17th century when the boundaries of knowledge were about to be expanded by the brilliant mind of one man, Cassini-Huygens, a polymath, a pioneer, a seeker of truth. Born at The Hague in April 1629 to a wealthy house in the orbit of the Dutch royal family, his father, Constantine Huygens, was a noted scholar and diplomat for the House of Orange and the Dutch royal family. As you can imagine, being able to share the room with aristocracy, he had access to a great education. Even though most of that was largely homeschooling, he quickly became somewhat of a prodigy among his family, who themselves weren't slouches. An artist friend of the family remarked on his skills with geometry. In 1655, he travelled to Paris, where he quickly established himself in the right circles. It was here his love of astronomy really blossomed, where he learned to build his own telescopes and even polish his own lenses, which in the evenings he used to observe the cosmos. Building a large telescope of sorts in his garden using a series of lenses that he made during the day slung from a tree and aimed using a system of pulleys connected between the lenses to a frame on the ground. It was with this rig that Christian Huygens discovered the moon Titan. Then in 1659, using the same system, he was able to deduce the actual three-dimensional shape of Saturn, that being a sphere with a flat disk around its equator but never touching it anywhere. Up until this point, people had been very confused as to its actual shape, as from our point of view, it changes perspective as the plane of the disk follows the equator, moving up and down due to the seasons caused by Saturn's axial tilt. Christian's work gave him a need for precise timekeeping, which became enough of a problem for him that he invented the modern pendulum clock, losing barely 15 seconds over a 24-hour span, whereas the next best clock was losing up to 15 minutes. Later in his life, he drew his work into that of the physics of light itself, with his main competitor being no other than Isaac Newton. Newton's chain of thought took him down a line of reasoning that light must be particle-like, while Huygens thought it to be much more wave-like. The two actually corresponded via letter on this topic. We now know centuries later that they were actually kind of both right. He wrote one last great intellectual piece, the Cosmotheros, a paper discussing his ideas on alien life before passing on July 8th, 1695. Huygens' life was a testament to the power of inquiry, a reminder that in our quest for understanding, we are all explorers of the cosmos, each of us a tiny fragment in the grand story of the universe. Cassini-Huygens was a labour of love. Thousands of scientists and engineers from NASA, ESA and ASI came together, united in their shared passion to explore a distant world. A system of moons and rings 1.3 billion kilometres away from Earth. This collaboration was an orchestration of international effort built upon decades of discovery. Engineers whose hands shaped delicate instruments, able to sense the faintest of whispers of particles and plasma in the empty void. These were not ordinary people. They were the dreamers who believed that through precision, through science, they could unlock the secrets of the gas giant Saturn. Let us reflect upon the people, the engineers, the scientists, the visionaries who crafted this remarkable journey. They're not just technicians, they were storytellers, weaving together the threads of curiosity and courage, each one playing a vital role in this symphony of exploration. Among them was Dr. Carolyn Porco, leader of the imaging team. With her relentless spirit and keen eye, she transformed the way we see Saturn. It was she who famously said that the most beautiful thing ever made by human hands is a photograph of Earth taken from space. Studying at Stony Brook and Caltech, where she focused on Voyager discoveries in the rings of Saturn, landing 2 great gigs in 1 year, a job at the University of Arizona, and she was also made a member of the Voyager imaging team. It was here that she helped plan many of the famous Voyager images, including being none other than that of the pale blue dot image made famous by Carl Sagan. With her profound understanding of imaging technology, Dr. Paul Curnow and her team captured breathtaking photographs that revealed an ethereal beauty of Saturn and its icy moons. These images were not merely just pictures, they were windows into the universe, sparking our curiosity and igniting our imaginations. Among her many contributions, Dr. Paul Curnow championed the exploration of Enceladus, the tiny moon choked in ice. With Cassini, we discovered the geysers erupting from its surface, streams of water, vapor, and organic compounds shooting into the darkness of space. Dr. Paul Curnow's work also illuminated the intricate dynamics of Saturn's rings, revealing them to be more than celestial debris. They are a complex, vibrant ecosystem of icy particles, each dancing to the gravitational rhythm of Saturn's moons. Her work, being very visual in its end product, was also drawn upon by Hollywood. She actually collaborated with J.J. Abrams for a shot in 2009's Star Trek reboot, featuring the Starship Enterprise emerging from warp in the upper cloud decks of Titan, with Saturn and its rings majestically hanging in the sky behind it. As we contemplate the beauty and wonder of Saturn, let us carry forward the spirit of exploration that Dr. Paul Curnow embodies. For the grand tapestry of the universe, we are but a tiny thread, yet each discovery we make leaves us closer to understanding our place among the stars. Then there was the indomitable spirit of Dr. Linda Spilker, a project scientist whose passion for Saturn and its moons drove her to explore the mysteries of Titan and Enceladus. Studying at California State University and then UCLA, where she specialized in planetary geophysics. She worked on the Voyager missions in a wide variety of roles, including but not limited to infrared radiometry and spectrometry and the compositional mapping of Jupiter's moon, Io. Dr. Spilker has been a part of the Cassini mission from its very conception, serving as a Cassini project scientist, guiding the team of dedicated researchers choosing which of Saturn's moons they actually wanted to explore. Her keen intellect and unwavering curiosity led to profound discoveries about this gas giant, which has captivated humanity for centuries. She helped the development of Cassini's infrared instruments and the mission planning for their usage. One of Dr. Spilker's most significant contributions was her work on that of Titan. Thanks to Dr. Spilker's leadership, the Cassini mission provided invaluable data revealing the complex chemistry of Titan's atmosphere and hinting at a tantalizing possibility of life beyond Earth. But the wonders did not end there. Under her guidance, Cassini unveiled the intricate structure of Saturn's rings, revealing their dynamic nature. Each particle of ice and dust, a silent witness to the passage of time, dances in a cosmic ballet shaped by the gravitational embrace of the planet and its moons. It was Dr. Spilker's insight that helped us understand the ephemeral beauty of this complex system. Her work also extended to the intricacies of Saturn's magnetosphere, where charged particles swirl and collide, creating a vibrant symphony of light. Through the Cassini mission, we glimpsed at the interplay between the solar wind and Saturn's enormous magnetic field. As we reflect upon the legacy of the Cassini mission, we celebrate not only the wonders it revealed, but also the spirit of collaboration and discovery embodied by Dr. Linda Spilker. Let us not forget the many engineers who tirelessly worked behind the scenes, their hands crafting the delicate instruments that would one day unlock the universe's secrets. Their dedication was a quiet force, a heartbeat that pulsed through every stage of this mission. One such engineer was Ralph Lorenz. Dr. Lorenz's contributions to the Cassini missions were not mere footnotes in a scientific ledger. As a member of the engineering team, he was deeply involved in the design and execution of the Huygens probe. Imagine, if you will, a tiny intrepid spacecraft parachuting through the clouds of methane and ethane, braving the harsh conditions of this distant world. It was Dr. Lorenz's expertise in aerodynamics that guided the probe's descent, ensuring that it navigated the treacherous winds and landed softly on Titan's icy surface. Titan, a world shrouded in mystery, revealed itself as a place of breathtaking landscapes where rivers of liquid methane carve their paths through a frozen terrain. Thanks to Dr. Lorenz's insights, we learn that Titan is not just a mere moon, it is a world unto itself, filled with the ingredients for potential life, echoing that of the primordial Earth. One of the parts of the Huygens probe that Dr. Lorenz actually personally designed and built is the penetrometer, a small finger-sized device that pokes out at the bottom of the spacecraft and as it lands, gets a reading of the density of the impact. Coincidentally, it was joked about by the media that Titan's surface has a creme brulee-like density in that it crackles at first, but is quite soft immediately underneath. By the media joked about the Huygens engineering team getting their just desserts. As we gaze upon the wonders of the cosmos, let us remember that the minds like Dr. Ralph Lorenz who dare to dream, who engineer the pathways to the stars. In their hands lie the keys to unlocking the cosmos, the secrets of worlds beyond our own, reminding us that the universe is vast and there is much left to discover. In its grand finale, Cassini plunged into the atmosphere of Saturn. The mission didn't really end there, per se. It transformed. It gifted us with knowledge, inspiring future generations to look up and wonder. So let us celebrate not only the spacecraft, but the people, dreamers and doers, who remind us that the universe is not just a mere collection of stars, it is a canvas for our imagination and exploration. What's the first thing that you notice about the spacecraft? What's missing that would usually be there? Because of Saturn's immense distance from the Sun, 10 times further than the Earth is from the Sun, solar arrays are not really feasible as a power source for a space probe out here. To generate enough power, solar arrays would have been far too large and too heavy. This machine was powered by 3 radioisotopic thermoelectric generators. These 3 generators use heat from the decay of about 30 kilograms of plutonium-238 to generate a directed current via thermoelectrics, the process of converting heat to electricity. At the end of its 11-year nominal mission, these RTGs were still actually able to produce 600 to 700 watts of electrical power. The primary spacecraft itself weighed in at about 6 tons and was approximately the size of a bus. Built by NASA, the spacecraft was planned to be a 3-axis stabilized RTG-powered Mariner Mark II class spacecraft, which was developed for missions to the outer solar system. Whilst being developed, Cassini actually had a twin, the Comet Rendezvous program, or CRAF spacecraft, but budget cuts and project rescopings forced NASA to terminate this other mission in order to save Cassini, which in turn became more specialized. While every single gram makes getting off of the ground a little bit harder, you really need to pick and choose what goes with you. And as such, you have to be very specific about the data that you'd like to collect and the instruments you're going to need to do so. In turn, those instruments need power, protection from physical damage and radiation, and a solid and stable physical base from which to aim at their potential targets. This core backbone platform is known as the Structural Subsystem, or STRU. The STRU consisted of mission flight computers and their electronics assembly, the reaction wheels, the high-gain antenna, which was also acting as a shield for most of the electronics assembly and the instruments, the primary mission pallet, which wrapped around the core of the spacecraft, the low-gain antenna, and the mag boom arm and the lower equipment module, structural mounting for the Huygens probe and the RTGs, the thrusters, and the primary engines, as well as the mount which fixed it to the rocket during launch. At the heart of this magnificent machine lies the propulsion subsystem, propelling our hopes and dreams into the unknown. The primary mission platform had 2 different engine subsystems on board which were tailored to specific kinds of movement. Most spacecraft are built like this because their systems work in completely different scales. System 1 is more than likely the one that you're expecting, with the primary rocket motor used for really big changes in motion like orbital insertion and major changes to orbits. This system uses bipropellant, nitrogen tetroxide and monomethylhydrazine. When mixed together, they ignite, and this produces up to 445 newtons of force for propulsive maneuvers. The main engine and its backup, which was surprisingly never actually used, are protected by a micrometeor particle shield. System 2 is for much smaller movements like changing roll, pitch and yaw. The system uses monopropellant hydrazine and is an array of 16 redundant 1 Newton thrusters with 4 per cluster. Any movement smaller than this can be handled by the reaction wheels, which are small rotating discs of heavy metal which can be used to counteract any rolling motion on any axis of the spacecraft. The instruments on board the Cassini spacecraft were research-led, as every gram of weight counted. Each area of research had a small suite of sensors available to them, and they included the optical remote sensing suite, which is located on the remote sensing pallet. An opinion of the late great Carl Sagan was that when you're spending billions of taxpayer dollars, you really do need to at least give them some pretty pictures. Some of the optical instruments were the composite infrared spectrometer, or CIRS, allowed us to peer into the invisible, the infrared realm. It captured the heat signatures of Saturn and its moons, revealing secrets hidden beneath the clouds of gas and ice. The imaging subsystem, ISS, a pair of cameras that could capture the universe in stunning detail. With its wide-angle and narrow-angle lenses, Cassini gifted us images that transcended mere data. It showed us Saturn's majestic rings, swirling storms in its atmosphere, and the enigmatic moons like Titan shrouded in its thick orange haze, and Enceladus and its icy plumes from beneath its surface. Each image was a window into worlds unknown, reminding us that we are part of something far greater. The beauty of these pictures are far more than aesthetic. They were clues into the hidden workings of our solar system and perhaps the cosmos itself. Ultraviolet imaging spectrograph, or UVIS. By capturing ultraviolet wavelengths, this instrument reveals the world invisible to the human eye. It allows us to peer into Saturn's auroras, to study the composition of its enigmatic rings, and to glimpse into the hidden chemistry of its moons, like Titan. The Visible and Infrared Mapping Spectrometer, or VIMS. VIMS was designed to look beyond what the human eye can see. Capturing light in both infrared and visible wavelengths, it allowed scientists to study Saturn's, its rings, and moons in unprecedented detail. One of the most impressive feats was mapping the thick, hazy atmosphere of Saturn's largest moon, Titan. VIMS revealed hidden lakes of methane beneath the clouds of Titan and unveiled a mysterious Earth-like landscape. VIMS also helped detect water, ice and compounds in the icy plumes of Enceladus, clues that suggest that this tiny moon may harbour conditions suitable for life. The Cassini Plasma Spectrometer, or CAPS. CAPS is a wondrous instrument aboard the Cassini spacecraft. CAPS listened to the plasma, the soup of energetic ions and electrons surrounding the giant planet and its moons, and even the magnetic field that stretches far beyond the planet's system. Like an ancient mariner setting sail on uncharted seas, this instrument detects the winds and currents of invisible particles that swirl through Saturn's magnetosphere. Each particle tells us a little story, a story of the sun's influence reaching across the vast gulf of space. It was through the plasma spectrometer that we actually first noticed that there was something weird around the moon of Enceladus. Basically, a giant lobe of some kind of distortion field that changed the dynamics of the magnetic field lines coming out of Saturn's poles. It was through closer inspection of this that we discovered that the plumes were there. The Cosmic Dust Analyzer is a device that humbles us with its exquisite purpose. This instrument, like a cosmic butterfly net, is designed to capture and study the minute particles of dust, ancient remnants of the solar system's formation, timeless wonders born on the winds of space. Each speck that it collects tells a story of the distant past and present, whispering secrets of collisions between icy moons, eruptions from the geysers of Enceladus, and the eternal dance of the particles within Saturn's rings. With remarkable precision, the Cosmic Dust Analyzer deciphers the composition of these dust grains, unlocking their elemental makeup, silicon, oxygen, and carbon, and revealing the forces that shape not just Saturn's realm, but the very nature of planetary systems themselves. The ion and neutral mass spectrometer samples gases with exquisite precision. It measures the mass and composition of ions and neutral particles, revealing their elemental and molecular makeup. In these readings, we discover not just cold data, but the stories of how these moons formed, how their atmospheres evolved, and whether life-sustaining ingredients may linger in the most unexpected of places. Through the ion and neutral mass spectrometer, Cassini allows us to glimpse the chemistry of alien worlds, and in doing so, it deepens our connection to the cosmos. The magnetometer aboard Cassini allowed us to peer into invisible worlds. Like a cosmic compass, it measured the magnetic fields around Saturn, revealing intricate interactions between the planet, the moons, and its majestic rings. It helped us map the planet's atmospheric environment in an unprecedented detail, tracing the flow of charged particles, tiny fragments of stardust trapped in Saturn's magnetosphere, swirling and dancing in a rhythm with the planet's mighty rotation. This instrument also detected something wondrous around the moon of Enceladus. Plumes of water vapor shooting into space from its icy surface were interacting with Saturn's magnetic field, leaving a signature in the data. The magnetometer provided the first hint of a hidden ocean beneath Enceladus' icy crust, a potential cradle for life. The spacecraft Cassini carries a remarkable instrument, one that allows us to see the unseen. It is the Magnetospheric Imaging Instrument, or MIMI, a tool that reveals invisible forces swirling around Saturn. MIMI was designed to capture images of its magnetic bubble, using energetic neutral atoms, ions, and electrons to paint a picture of this exotic world. As the particles collide and interact, they tell a story of solar wind, of Saturn's moons, and even the planet itself. Within its data, MIMI showed us that how the magnetosphere is influenced by the sun's charged particles and how Saturn's moon Enceladus ejects material that contributes to this invisible environment. Through MIMI's eyes, we see the interplay of cosmic forces in a way that no human could, reminding us once again that the elegance and complexity of our universe, as Carl Sagan once said, something, somewhere, incredible is waiting to be known. And the MIMI instrument is helping us know that. Cassini's radio and plasma wave science instrument suite, it picked up on radio emissions from around the planet, its rings, and even its moons, particularly the icy world of Enceladus. It traced the movements of charged particles, plasma, from within Saturn's immense magnetic field. From the low hum of Saturn's radio waves to the burst of energy from its auroras, it was a cosmic eavesdropper, revealing the chaotic, beautiful interplay of forces that shape the very structure of Saturn's environment. Through these delicate signals, we learn that Saturn's magnetic field, like Earth's, traps particles from the solar wind, creating a stunning dance of charged particles, plasma waves, and electromagnetic radiation. The RPWS showed us how the solar wind interacts with Saturn's magnetosphere, a complex ballet that gives rise to magnificent ethereal auroras around the poles. Microwave remote sensing. While the visible light shows us the beauty of Saturn and its rings, it's microwaves that unlock the secrets hidden beneath the surface. Cassini's microwave sensors, such as its radar, pierce through the thick, swirling clouds of Titan, Saturn's largest moon, revealing the landscapes of frozen methane and lakes and ancient ice dunes below. But how does it work? Building images by sending radio waves, like a distant voice calling out, and then listening for the echoes as they bounce back from the planet and the moon below. From the time it takes for those distant waves to return and how they change, we can map entire worlds, measuring the composition of their surface and understanding their temperatures. Microwaves that have a unique ability to penetrate deep, allowing Cassini to see through the fog of Titan or detect the heat emanating from the depths of Enceladus. In this way, Cassini's microwave remote sensing doesn't really just observe, it explores, unveiling layers of reality that our eyes could never see. It is a testament to human curiosity and enduring desire to understand the vastness of the cosmos. The Huygens lander. Built by ESA and the Italian Space Agency, the Huygens lander was a small 1-meter atmospheric entry probe designed for many different environments. Because of Titan's thick haze, we really did not know what kind of surface that the Huygens lander was bound for, or even if there was actually a surface at all. So the team planned for a hard surface landing, but also ensured that the lander was light enough to float in the predicted liquid hydrocarbons. For 7 long years, Huygens journeyed through the vastness of space. Then, on December 25th, 2004, it was released from Cassini's grasp, coasting for 20 days before plummeting through the outer atmosphere of Titan. There it fell, slowly descending through the sky unlike anything we have ever known. The thick, nitrogen-rich atmosphere tugged at its parachute, slowing its descent as it began to explore the layers of this alien world. Then, in 2005, the probe became the first man-made object to land on a moon in the outer solar system. Again, just like its parent spacecraft, the Huygens lander was pretty restricted in terms of what it could take with it. The aerosol collector and pyrolyzer, or ACP, was tasked with sampling Titan's thick atmosphere, an atmosphere dominated by methane and nitrogen. As it descended through the haze, the ACP would capture particles and analyze them, and reveal the very composition of Titan's air. Perhaps within these elements we would find clues to the chemistry of prebiotic life, offering a glimpse of what Earth's atmosphere may have been like in its infancy. Then there was the gas chromatograph mass spectrometer, GCMS. A scientist's dream in miniature, this device is no larger than a briefcase, could analyze gases and organic molecules with incredible precision. It was destined to tell us not just what was present, but how those molecules formed and what processes shaped Titan's chemical evolution. The Surface Science Package, or SSP, was like a set of eyes and ears for Huygens. It would measure air pressure, density, and the behavior of Titan's surface materials. Was it solid, liquid, icy, or perhaps something in between? The SSP would feel the ground beneath the probe, sending back data that would allow us finally to understand this strange landscape. The Descent Imager and Spectral Radiometer. One of the most fascinating tools aboard the Huygens probe was the Descent Imager and Spectral Radiometer, the EISR. As Huygens fell through Titan's clouds, this instrument would take pictures, offering a first-hand view of what no human eye has ever seen before. It would also study the sunlight scattering in Titan's atmosphere, unlocking the secrets of Titan's climate. For a few precious hours, it transmitted data back, showing us a place that was once both alien and eerily familiar. Titan, a world sculpted by chemistry, time, and the forces we are only beginning to comprehend. A world where rain falls, but not as water, as methane. A world where beneath the ice there may be a water ocean, a deep reservoir of liquid water, perhaps harboring the potential for life. What Huygens revealed to us was more than just data or images, but a profound reminder of our own insignificance in the grand cosmos and our remarkable capacity to explore it. Through the eyes of our machines, we stand on distant shores, gazing into the unknown. The rocket. The Titan 4B was designed by the Martin Marietta Corporation and was commonly used by the US Air Force from 1989 to 2005. The design was launched 39 times, with only 4 of those launches being unsuccessful. The Titan 4 booster was the last of the Titan suite of rockets, which was originally developed by the Glenn L. Martin Company in 1958. It was retired in 2005 due to its high cost, approximately $500 million to launch, and its use of potentially toxic propellants. It was later replaced with the Atlas V and the Delta IV. Lockheed Martin Space Systems constructed the Titan 4s near Denver, Colorado. The Titan 4 could lift about 21 tons to low Earth orbit. Stage 0 consisted of 2 solid rocket motor boosters. Stage 1 used a liquid propellant rocket engine, and Stage 2 also using liquid propellants. Rocket Stage 2, the Centaur. The Centaur is a family of upper stage rockets used to go from Earth orbit and put the spacecraft on track to its target. It is produced by the United Launch Alliance. It has a long history of use, including being launched from the cargo bay of the Space Shuttle. The Centaur concept originated in 1956 by Convair while they were studying liquid hydrogen-fueled upper stages. Convair continued the project under the Advanced Research Project Agency, or ARPA, which later became DARPA. The Centaur T was launched 9 times between 1994 and 1998. The launch. Launch Complex 40, Kennedy Space Center, Cape Canaveral, Florida, the USA. October 15th, 1997, 8:43 a.m. local time. Now, see, rocket science isn't known as complex only for the tyranny of the rocket equation. Once you get away from the Earth, you then need to contend with everything being moving. This is the science of orbital dynamics, and it offers some interesting opportunities for cheaper travel. En route, Cassini encountered Venus twice, Earth once, and the asteroid 2685 Mercury, and finally Jupiter. Each encounter added slightly more velocity to the spacecraft so that it could keep all its onboard fuel for its deceleration and orbital capture at its final destination. Even with extra help, this journey took 11 years. In 2002, it did tests passing a radio beam close to the Sun and measuring its gravitational deflection, confirming relativity down to a resolution 50 times better than known via earlier measurements. At the end of 2004, the spacecraft was close enough to get better shots of Saturn than Earth-based telescopes. In 2008, Cassini entered Saturn's Hill sphere, where a mass becomes the dominant gravitational body in the area. It's here that orbital insertion begins, but it cannot simply glide into orbit. In order to be captured by Saturn's gravity, Cassini must slow itself down in a delicate, controlled maneuver. At this point, Cassini was travelling at an astonishing velocity, approximately 22 kilometres per second. The spacecraft was moving too fast to naturally enter the orbit around Saturn. It would simply fly by. The spacecraft's thrusters fired in a carefully timed sequence, burning the main engine for around 96 minutes and consuming 822 kilograms of onboard propellant. It was a controlled blaze, designed to slow Cassini down to ease its passage into the embrace of Saturn's gravity. The goal was to reduce its speed to around 6 kilometers per second, a drastic but essential deceleration to approximately 21,600 kilometers per hour, allowing it to be captured by the planet's gravitational field, and so, in slipping into Saturn's gravitational embrace, Cassini, guided by the careful calculations from Earth, performed this delicate maneuver flawlessly, setting up its first few orbits to have multiple flybys of Titan where it would drop off the Huygens probe. At the time of researching this presentation, there have been more than 4,000 scientific papers published off the back of the 635 gigabytes of scientific data gathered during this mission. Discoveries about the atmosphere, weather systems, and magnetic field of Saturn were plentiful. Astronomers for a long time have struggled to pin down the length of Saturn's day, as there are no real landmarks at all. Saturn's surface, if you could call it that, is nearly all uniform cloud bands of hydrogen and helium, getting denser and denser until the hydrogen reaches a density where it forms what's referred to as a metallic liquid. There may be a rocky core somewhere, but is beyond our reach. Up until this mission, we only had an approximate of its rotational speed, which was worked on by Cassini to within minutes of the actual modern measurement. Where Jupiter has the great red spot as a marker that makes it much easier to track the day length as opposed to Saturn. This was up until Cassini. Just after orbital insertion, something absolutely remarkable happened. Within the first weeks of arrival, a giant, and I do mean giant, storm erupted out of nowhere from Saturn's lower atmosphere, growing a bizarre tail-like structure until it wrapped nearly all the way around the planet entirely before its tail hit the front of it and caused it to dissipate. But before it did, we took a lot of data. It was an extremely energetic weather event, quite significantly raising the temperature of the local atmosphere of Saturn. This storm was not the only interesting atmospheric phenomena we saw there either. There is a giant hexagon shape in Saturn's north pole. This formation seems to happen due to Saturn's jet stream, and there are similar structures on most planets, but nowhere else in the solar system you'll find something that is uninterrupted and therefore forms this near perfect hexagon shape. Some of the other things we looked into was the odd phenomena of Saturn's temperature, as it seems to radiate 2.5 times more energy in the infrared than it receives from the sun, and that our current hypothesis, based off the data from Cassini, is that there is friction caused in the lower reaches of the atmosphere between atmospheric decks that causes friction, which needs to be dissipated through the atmosphere. Also, like most other planets, Saturn's magnetic field is not actually aligned to its axis of rotation, which, like Earth's, it precesses over time. The particles within the rings range in size from that of smoke all the way up to moons and planetesimals. The idyllic rings are a much more dynamic environment than we initially thought, something that became apparent to us the closer that Cassini got to them. While from our vantage point on Earth, the rings can look almost two-dimensional, they are anything but. Having an average thickness of around 10 to 20 meters for most of the system, there are actually what can only be described as waves and mountains of dust pulled above and below the ring plane by moonlets and small bodies embedded within the system itself. It's these shepherd moons and their interactions that are responsible for the rhythmic gaps and structures within the system as a whole, organising the system into its iconic bands. Several of these shepherd moons, like Pan, have a really unique feature, that of an equatorial mountain range, and it actually extends quite significantly out into the void, giving it an unnatural visual appearance. Saturn and its surroundings is one of the most complex regions of our solar system. At the time of writing this, we currently know of about 146 moons. These moons range in size from merely a few meters across all the way up to the second largest moon in our entire solar system, which is actually larger than the planet Mercury. While at the time of their discovery, most of Saturn's moons were just given names like Saturn 1 and 2, and it was actually the son of William Herschel, John Herschel, who came up with the system of naming that we use now. He gave them names that were associated with the Roman Titan of time, which is also Saturn, and named several of the satellites after the Titans. And after the names of these Titans were exhausted, they switched to characters from Greco-Roman mythology. Are Saturn's majestic rings a permanent feature or something more ephemeral? At this stage, it looks as if the rings are actually quite a young feature and that they may eventually fall into Saturn over the next billion-ish years. We now have another question about the whole inner Saturnian system. Did the current arrangement arrive via this slow cumulative build-up at Saturn's birth, or did a moon wander too close to the planet and get pulled apart? Major gravitational bodies have multiple domains of influence, one being its Hill sphere. Where a planetary body is a primary regional mass, it also has what's called the body's Roche limit. The Roche limit is a cosmic boundary drawn not in ink, but the silent hand of gravity. A planet, mighty and serene, pulls the very fabric of its surroundings. When a celestial body, perhaps a moon, ventures too close, the gravitational forces become unforgiving. The pull of the planet, stronger than the moon's own cohesion, begins to tear it apart. Here, with an invisible limit, a moon becomes rings. The solid worlds crumble to dust. It is a reminder within the vast universe there are boundaries we cannot see, but they shape the destinies of worlds. We all know that moons orbit planets, but it's not actually that simple. The Lagrange points of semi-stable gravitational equilibrium where small objects can be captured and pushed or pulled along with the primary body at L4 and L5, both areas being 60 degrees either ahead or behind of the primary body in its orbit. Something that is an ongoing study as to why Saturn does not appear to have any Trojans. As you can imagine, there are many sub-classifications of moons that we need to take into mind around Saturn. Some of them include small ring moonlets and shepherds where they're embedded within the ring system itself. We have co-orbitals where we have two bodies sharing the same orbit but not necessarily pulling each other toward each other. Then we have inner large alkaloid Trojan, outer and irregular moons. Irregulars just being simply more or less captured asteroids or cometary bodies that wander too close. Another interesting natural solution to the complexity of what is known as the three-body problem is that orbital resonance, where orbital speeds of multiple bodies will be in resonance with each other. This is common in planetary systems with large numbers of moons. The moons will end up having fixed ratios in that the orbits will be completed in the same time period. Take, for example, Saturn's moons Mimas and Tethys. They share an orbital resonance of 2 to 1. For every 2 orbits Mimas completes around Saturn, Tethys finishes 1. Their gravitational tugs pull on each other, though faint, accumulate over time, guiding their orbits in a synchronized rhythm. Further out, we have the trio Enceladus, Dione, and Rhea, all bound together in another orbital resonance. Enceladus orbits Saturn twice for every orbit Dione completes, and Dione orbits Saturn twice for every orbit of Rhea. It's although these moons are partners in a cosmic symphony, their gravitational pulls working together in a delicate cosmic balance. It is currently theorized that the Cassini division is actually caused by an orbital resonance with the particles therein and the moon Mimas. But resonance is more than just a mathematical coincidence. It shapes the moons themselves. Take Enceladus, for instance. Gravitational interaction with Dione creates tidal forces within Enceladus, heating its interior. Orbital resonance is one of the universe's subtle ways of creating order out of chaos. It tells us that even in the depths of space, there is harmony. A kind of music on a grand scale beyond our comprehension. Titan is the largest of Saturn's moons and the second largest moon in the solar system, only beaten by Jupiter's Ganymede. It is actually larger than the planet Mercury and the only moon in the solar system to retain a significant atmosphere. Water is abundantly present on Titan's surface, but only as its rock layer, its crust. Like many bodies in the outer solar system, Titan is thought to have a large subsurface liquid water ocean mantle, where there is a water ammonia ocean separating the core from an outer shell. The polar regions of Titan have a feature unique to this large moon, and that's liquid. As far as we are currently aware, it's only Earth and Titan that both have an atmospheric pressure range for stable liquids on their surface. Titan's atmosphere is about 4 times more massive than Earth, but due to the lower mass of the moon compared to that of Earth, it equals out to a density approximately only twice that of Earth at its surface. This, coupled with Titan's frigid temperatures, allow for stable liquid hydrocarbons like methane and ethane to exist in large bodies, the largest of which we have called Kraken Mare after the mythical sea monster of Earth's maritime history. The next largest 2 are Ligeia Mare and Punga Mare, which all exist at Titan's northern pole. These lakes are of similar size to the Northern American Great Lakes or Caspian Sea. These bodies are fed by rivers and tributaries in a very similar manner to the water cycle of Earth, but at a much slower rate, as a Saturnian year is that of about 29.4 Earth years. Titan is, of course, pulled around the Sun by Saturn, while its day takes only 16 Earth days to complete. Both Titan and Saturn are slightly inclined in their orbits, and as such, Titan experiences seasons, in the same way that Earth does. Most of these lake clusters are on the moon's northern polar region, while the equatorial region has a huge area of Tholen dunes. After spectrographic readings of Titan's atmosphere, they put together an experiment where they took the chemicals they thought to be in existence there and put an electrical charge through it. The material that collected in the bottom of the experiment was full of the precursor chemicals to amino acids, and they called this chemical Tholen. Cassini took both radar and infrared images and data of the lakes, and they appear to have extremely smooth surfaces, which is odd because the wind there should enable the production of small surface waves. This raises some questions about the liquid viscosity. The before-mentioned readings allowed us to deduce that Titan does in fact have tides like Earth, but they are very, very small. Titan's methane and nitrogen atmosphere has a meteorological cycle where it rains and snows hydrocarbons. Dr. Ralph Lorenz describes such features as a methanogenic monsoon, where the atmosphere can hold quite a lot of liquid vapor methane, and it can build up for quite long periods of time, maybe even centuries between rain events, and these come out in a similar fashion to what is known on Earth as a rain bomb. As Cassini completed its primary mission, it was actually extended twice. This enabled much further and better exploration of the moons. As the mission was extended, it gave the team the opportunity to put multiple passes over Titan's north pole and that of Ligeia Mare. It was there that they found a landmass several hundred square kilometres across, and surprisingly enough, it actually wasn't there in previous passes. Now, we're viewing this at orbital speed and through a thick, opaque atmosphere, but this looks like a transitory floating mass within the hydrocarbon sea. Now, we don't know whether these structures are similar to that of a pumice raft on Earth, where volcanic ejecta is erupting from a mountain on the seafloor and spewing gas-filled rubble, which then creates a kind of like a floating island-looking structure out at sea. We don't yet know what this mysterious structure was, as the dynamics of how things float within liquid hydrocarbons are not yet particularly well understood. We currently also theorize that some of these hydrocarbon lakes may be very stratified in the chemical composition, in that they may change quite significantly, in that there may be strata of ethane and methane that goes down quite deep, and it's possible that this goes deep enough to potentially puncture and interact with the water ice ocean layer beneath the frozen water crust of Titan. And it's going to be very interesting when we go back to see whether we can find more about that. Enceladus is the 6th largest moon of Saturn and the 19th largest in the solar system. It is about 500 kilometres across, but it boasts the title of being the most reflective object in the solar system. With 90% of the light that hits it is reflected back out into space. This is because its surface is nearly 100% water ice, from pole to pole, kilometres thick, and it actually appears to be floating on a liquid water ocean. The truly unexpected find of the mission was water, and better yet, water that we can access. Enceladus is a mysteriously smooth body for how far it is in the outer solar system. Most of its brethren are pocketed with a stunning array of crater scars. This meant that the surface was somehow either being eroded or renewed through some kind of geological or tectonic process. As the probe came towards Enceladus for the first time, it got a really, really odd reading from the magnetometer. It turns out that the magnetic field emanating from Saturn's poles was being bent around some kind of large lobe-like structure around Enceladus's southern pole, disturbing it in a way that it shouldn't. It was then that they really needed to get some visual references for what was happening at this tiny moon. And it's when they came around orbiting from the back and viewing Enceladus being backlit from the sun that the absolutely magnificent discovery took place. What we saw there was absolutely stunning. 4 huge rift valleys. We've called them Damascus, Baghdad, Cairo, and Alexandrina, out of which huge geysers were spewing vast amounts of water up into space, tens of thousands of kilometres into space. Some of this material was falling back onto the small moon, which duly accounted for why the body is so smooth. The rest of it was ejected and falling out into orbit around Saturn, which fuels and feeds one of Saturn's most faint rings, which can only really be seen when the planet is eclipsing the sun. This proved that there was liquid water under the icy shell of the body. While the small porous rocky core is being flexed due to its elliptical orbit and interactions with its neighbours, this heats up the rock enough to have a stable liquid water ocean kilometres deep underneath a thick ice layer similar to Earth's poles. This ice layer varies in thickness, but it is thought to be about 5 to 20 kilometres thick. While it could be that gravitational interactions or maybe a large meteorite collision have produced enough heat locally at the South Pole to create a small regional ocean due to the way that Cassini's orbit got bent around the small moon, we do believe the ice moon does cover a global sea, which is then in turn interacting geologically with heat being poured out of a small rocky porous core, producing an environment which is believed to be similar to Earth's black smoker phenomenon on the sea floor, which could potentially be a place where chemosynthetic life could exist. These huge geysers being spewed out into space offered an extremely opportune moment in that we could use Cassini's cosmic dust analyzer and directly sample the particles being spewed out into space. And for the most part, they are different concentrations and different sized grains of water ice with small bits of silicate particulates at the core of the larger ones. That's right, we flew the craft directly through the plume multiple times, skirting Enceladus's south pole by a mere 12 kilometres at one point. Besides Earth, we don't really know of any other places within the solar system that may harbour life, but it looks like the Saturnian system is a really interesting place to continue our explorations on this front. Both Titan and Enceladus have at least a lot of similarities to that of early Earth, and I think that they are going to both be very, very fruitful in terms of scientific data coming up. As we spoke about earlier, the mission was nuclear powered. This battery could have powered the mission for much longer, but without any propellant left for its thrusters, NASA could not really guarantee that the spacecraft would not eventually crash into one of the moons and potentially contaminate any life that existed there, and we do take this extraordinarily seriously. So its last few orbits were given the parameters to do something a bit more daring, and it's actually skirted directly in between the planet and the ring system, eventually tightening the orbit so much so that the spacecraft entered Saturn's upper atmosphere. The mission, sadly, coming to its physical end on September 15th, 2017, as it plunged into Saturn's upper atmosphere, burning up in streaks of plasma. It was here that the spacecraft would burn up, forever becoming a piece of Saturn and locking in its place in our cosmic history. We live in a time when human ingenuity has reached far beyond our fragile Earth to touch the mysteries of another world. The Cassini-Huygens Mission, a partnership between humankind and the cosmos. For 13 years, Cassini orbited Saturn, unravelling its rings, moons and magnetosphere. In totality, the mission generated about 635 gigabytes of data and took 453,000 odd images, most of which would look great, framed and put up on a wall. They're going to be an inspiration for centuries to come. For the first time in history, we landed on an alien world, so distant yet curiously familiar. Huygens sent back echoes of a frozen realm with rivers and lakes, not water, but liquid methane and ethane, slowly flowing through the vast plains of hydrocarbon sand. Beneath Titan's hazy skies, we found an Earth-like environment frozen in time. The frigid temperatures, familiar in processes like rain, erosion and rivers, unfold in unfamiliar ways, sculpting a world that parallels our own in eerie ways. We glimpse the lakes and seas large enough to stretch beyond our comprehension, dunes that resembles that of Earth but yet made of entirely different materials. Titan is a paradox. A world where both alien and the familiar coexist in harmony, waiting for us to understand. And here it is, beneath the cloak of its dense atmosphere, we suspect even greater wonders may lie. A possibility for an ocean water beneath its icy crust. Our story with Titan is actually far from over. Now, humanity turns its eyes to the future with the upcoming Dragonfly mission. A butterfly in a distant meadow, Dragonfly will take flight in Titan's thick atmosphere, hopping across the vast distances to explore new and unknown regions. This rotorcraft will traverse the moon's surface, gathering clues about Titan's chemistry and potential for habitability. What lies beneath those icy plains? Could there be the raw ingredients for life, or maybe even life itself? With Dragonfly, we will explore Titan as never before, up close and mobile, free to roam across the enigmatic landscape. This mission will peer into the building blocks of the organic chemistry and search for answers for the greatest question that has driven us since we first gazed into the stars. Are we alone? Titan, with its rich complex chemistry, its liquid seas and possible subsurface ocean, may one day give us the answer we seek. As we await Dragonfly's first flight into this distant world, let us reflect on the legacy of Cassini-Huygens. It has shown us that the cosmos is not really an empty void, but a place of unimaginable beauty and diversity. Each mission, each discovery teaches us more about the universe and our place within it. We are the explorers, standing on the shores of the cosmic ocean. And Titan is one of the next destinations on our journey to the stars.